This presentation is part of the TI in Focus AP Calculus video series. In this video, I'll discuss the solutions, relevant concepts, and scoring guidelines associated with some of the parts of our 2020 mock AP Calculus exam, Form BC, Question 1. My name is Steve Kokoska. I'm a recently retired professor at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Form BC Question 1 involves the graph of g prime, the derivative of a twice differentiable function g. The graph of g prime has exactly one horizontal tangent line in the interval -1 to 10 at x equals 4.2. The plane region R is in the first quadrant and is bounded above by the graph of y equals g prime of x, below by the x-axis, and on the left by the y-axis. And we also know that g of 0 is equal to -7, g of 9 is 12, and the definite integral of g of x from 0 to 9 is 27.6. In part I, the region R is the base of a solid. The cross-sections perpendicular to the x-axis at an arbitrary value x are right triangles with height x and base in the region R. The volume of the solid is given by the definite integral of a of x from 0 to 9, and we need to find an expression for the function a of x. The key concept needed to solve this problem is a definition of volume, but we also really need some problem-solving skills here. Suppose S is a solid that lies between x equal a and x equal b. If the cross-sectional area of S in the plane P sub x through x and perpendicular to the x-axis is capital A of x, where a is continuous, then the volume of S is given by this definite integral. This is a very general definition of volume, and I usually use this to derive the formula for volume by disks and volume by washers. The real skill in these general types of problems is the ability to find an expression for capital A of x from the description of the solid. Here's an illustration of this definition. The solid S is shaded blue. The plane P sub x passes through x and is perpendicular to the x-axis. The intersection of the plane P sub x and the solid S is the green shaded region, and capital A of x represents the area of this region. This definition tells us that if we can find an expression for a of x, then we can use a definite integral to represent and then find the volume of the solid S. So, to solve this problem, we simply need an expression for a of x. I'm going to sketch a graph of the intersection of the plane P sub x and the solid S. That is, an arbitrary cross-section of the solid perpendicular to the x-axis. In my graph, this is the green shaded region. At x, the intersection or cross-section is a right triangle with height x and base in the region R. So the length of the base is the value of the function g prime of x. Therefore, a of x is 1/2 times the base times the height, or 1/2 times g prime of x times x. Here are the scoring guidelines for part I. This problem is worth 1 point, simply for the correct expression for a of x. And here are some interpretations of these guidelines to help understand how points are earned. If the student writes the entire definite integral with the correct integrand, that is, the correct expression for a of x, they must equate this to the definite integral with a of x as the integrand. And the reason for this is that if a student writes only the entire definite integral, that expression is interpreted as, well, their expression for a of x. So, a response like this earns the point. Now, the student may introduce another variable or function, and as long as definitions are clear, they can still learn the point. And here's an example. And this is a common error, equating a of x to the definite integral, and this does not earn the point. In part J, the student needs to find the volume of the solid described in part I. Therefore, they'll have to evaluate a definite integral, and the student needs to show the computations that lead to the answer. In order to solve this problem, we'll need to use integration by parts. And here's a little background information. Every differentiation formula has a corresponding integration formula. And the rule that corresponds to the product rule for differentiation is called integration by parts. And let's see exactly how to derive this from the product rule. Start with the product rule. The derivative of f times g is f times g prime plus g times f prime. Then use the notation of definite integrals. This equation becomes, well, this. Now I'll use a property of integrals. The integral of a sum is the sum of the integrals. And then finally, I'll just solve for one of the integrals. And this expression is the formula for integration by parts. It's probably easier to remember and use this formula by using the following notation. Let u be f of x, then du is f prime of x dx. And let v be g of x, and then dv is g prime of x dx. Then the integration by parts formula can be written as the integral of u dv is u times v minus the integral of v du. Let's take a quick, closer look at this formula. First, what's the purpose of this formula? Well, we use this to write a complicated integral in terms of another, hopefully easier integral. Therefore, the choices for u and dv are important and take practice and good pattern recognition. We want to select dv so that it can be integrated easily. And in general, we want to choose u so that the remaining integral, v du, is simpler than the original integral of u dv. To find the volume of the solid described in part I, we need to evaluate this definite integral. I'll bring the constant 1/2 through the integral sign, and I'll work with the remaining integral. Now we don't have an analytical expression for g prime of x, so a good technique here is to try integration by parts. We need to choose u and dv in a judicious manner. I'll let u equal x. I can find the derivative of x pretty easily. And dv has to be the remaining part of the original integral, g prime of x dx. And although I can't get an algebraic expression for the integral of g prime of x, an antiderivative is g of x. And I know a little bit about g as given in the problem. So I feel like these are good choices for u and dv. So the volume is equal to 1/2 times u times v minus the integral of v du. Let me just remind you that we can combine the formula for integration by parts with the fundamental theorem of calculus part 2 to evaluate integrals by parts. So we need to evaluate x times g of x at the upper and lower bounds and subtract. And the remaining integral is simpler, and the value of this definite integral was given in the statement of the problem. G of 9 is also given in the statement of the problem, and a little simplification gives us a final answer of 40.2. Here are the scoring guidelines for this problem. Part J is worth 2 points. 1 point for correctly applying integration by parts, and 1 point for the final answer. And here are some interpretations of these guidelines to help understand how points are earned. If there is no evidence of integration by parts in the solution presented by the student, then no points are earned in this part. The first point is for integration by parts, but without concern for the bounds. The limits of integration are associated with the answer point. And as I've talked about previously, there is often minimal work necessary to convince us that the student has used integration by parts correctly. Notice that the constant 1/2 is associated with the answer point. In Part K, the student needs to find the value of this definite integral or show that it does not exist. Now, the important thing to recognize here is that the integrand is not continuous over the entire interval 0 to 9. Using the original graph, g prime of 9 is equal to 0. So the integrand is not defined at x equal 9 and is therefore discontinuous. We cannot evaluate this in the usual way using the fundamental theorem of calculus part 2. While we're here, I just wanted to add a little background or motivation for how we evaluate this type of integral. So let's suppose f is a positive continuous function defined on a finite interval a to b, closed at a, open at b. And also suppose that the graph of f has a vertical asymptote at x equal b. Let R be the unbounded region below the graph of f and above the x-axis between a and b. So the region R is infinite in the vertical direction. The area of the part of R between a and t, in my graph this is the area of the blue shaded region, is the definite integral from a to t of f of x. And we can find this value in the usual way, using the FTC. And it seems reasonable to evaluate the integral of f of x from a to b by examining this definite integral, letting t get closer and closer to b from the left. If this value approaches a definite number as t approaches b from the left, then we express this result mathematically using this limit notation. And this expression is used to define an improper integral of type 2, even when f is not a positive function, no matter what type of discontinuity f has at b. Here's the formal definition of an improper integral of type 2. Now, I won't read through this entire definition with you, but I would just like to remind you that evaluating a type 2 improper integral is, in my opinion, a two-step process. First, we need to evaluate a definite integral, and then we need to evaluate a limit. Part C of this definition addresses the issue of a discontinuity at C in the interval a to b, not at an endpoint. Note that if either one of these integrals on the right diverges, then the original integral diverges. Let's use this definition of a type 2 improper integral to solve this problem. Now, the student needs to recognize that the integrand is discontinuous, and therefore that this is an improper integral. So, for me, that's my first step: recognition of the improper integral and use of the proper notation to determine convergence or divergence. So now we need to evaluate the definite integral. Now, there really is a U substitution going on in the background, but most of our AP Calculus students are so good at this basic anti-differentiation rule that they can see du over u, and they probably will not present the formal substitution process. And they really don't need to present the formal process, but they might want to in order to earn partial credit in the event of an error in the overall solution. So the antiderivative is the natural log of the absolute value of g prime of x. We really don't need the absolute value symbols here because g prime of x is greater than or equal to 0 on the interval 0 to 9, but I'll include them anyway. I just think it's good practice to use the most general antiderivative and then address the absolute value when we plug in the bounds. In this case, a student would not be penalized for excluding the absolute value symbols. Notice that I'm dragging along the limit notation because I have not executed that step yet. Remember, proper notation and good communication is important. So now plug in the bounds. G prime of 0 is equal to 1 from the graph, and the log of 1 is 0. So I'm left with this limit. As t goes to 9 from the left, g prime of t goes to 0 from the right, and the natural log goes to minus infinity, and therefore the original integral diverges. Here are the scoring guidelines for Part K. This problem is worth 3 points. This first point is earned for recognizing and properly conveying that this is indeed an improper integral. In general, that means that there must be an appropriate limit presented. The second point is for the antiderivative involving the natural log function. And the last point is for the answer. Here are some interpretations of these guidelines to help understand how points are earned. Again, no evidence of an explicit substitution is needed. This is a pretty basic anti-differentiation rule, and most students will recognize this right away. And the absolute value symbols are not necessary here. If the student makes an error in the limits while using a U substitution, they cannot earn the answer point, but they're still eligible for the first 2 points. If there is absolutely no evidence of an improper integral, then the maximum a student can earn here is 1 point, the antiderivative point. Limit notation must be used in order to earn the improper integral point, and the student must earn the improper integral point to be eligible for the answer point. The student can earn the antiderivative point working only with an indefinite integral if they choose. As an aside, my experience suggests that in this type of problem, many students fail to recognize this expression as an improper integral, and some end up trying to do ordinary arithmetic with infinity. And that should be a tip-off that something is wrong, and that maybe the original expression is an improper integral. In the last part of this free response question, we're given some extra information about g double prime of 0. And we need to find the second degree Taylor polynomial for g about x equals 0. Now, we could spend a whole month talking about Taylor series and Maclaurin series, but here's the basic concept needed to solve this problem. It says that if a function f has a power series expansion at a, then it must look like this. This is the Taylor series of a function f centered at a. The special case when a equals 0 is called the Maclaurin series, and the form of the series is given here. Knowing the general form of a Maclaurin series, solving this problem is pretty straightforward. Here are the 3 values we'll need. G of 0 is equal to minus 7, well, that's given in the statement of the problem. G prime of 0 equals 1, and we can read this from the given graph. And g double prime of 0 is equal to 0.7. That's given in the statement of this part of the problem. So here's the general form of the Taylor series of degree 2 centered at a equals 0. Or more specifically, the Maclaurin series of degree 2. Here I'll use the values of g of 0, g prime of 0, and g double prime of 0. And although not necessary for full credit, I'll simplify just a little for this final answer. Here are the scoring guidelines for Part L. This problem is worth 2 points. 1 point for conveying the correct form of the second degree Taylor polynomial centered at 0, and 1 point for the final answer. Here are some interpretations of these guidelines to help understand how points are earned. For the first point, we want to see the correct form of the coefficients and the corresponding powers of x. And only polynomials centered at x equals 0 are eligible for any points in this problem. If the student includes terms of degree greater than 2 or adds a plus ... to their presented Taylor polynomial, they cannot earn the second point. But they can still earn the first point for the form of their first 3 terms, but they cannot earn the second. If the student makes an error in simplification, they do not earn the second point. And this suggests again that students should not simplify final numerical answers. And finally, in this case, it's okay to call this second-degree polynomial almost anything, like q of x, or r of x, or even g of x. However, the student cannot equate this polynomial to a specific value, like g of 0 or t sub 2 of 0. This would not earn the answer point. I hope this video gives you a good idea of how to solve these problems using the necessary AP Calculus concepts, and a reasonable expectation of how they would be scored. This video concludes BC free response question number 1.